Today, I would like to talk about our recent research topic related to the assembly of the modular RNA enzyme. And before starting my talk, I would like to introduce the collaborator of this project. All biochemical experiments were done in University of Toyama by the 4 graduate students, and the AFM imaging were observed in Kyoto University by Professor Masayuki Endo's group. And the RNA world hypothesis is the most well-known hypothesis in the early stage of the RNA world, in which the self-replicating ligase ribozyme can join its own fragment, serve as the central part of the self-replicating system. And this ribozyme may evolve to catalyze various types of the chemical reaction related to the nucleic acid to expand the RNA world. And to sustain and develop this world, you can easily understand that the concentration of the RNA component, including the catalyst and substrate, is very important matter. If the RNA concentration is high enough, this replication proceeds smoothly, and the rare variant emerged during the era of the nucleotide replication can cultivate it. So this system successfully grows and evolves to the improved world. But in contrast, if the RNA concentration is low, replication efficiency is poor, and the RNA may degrade hydraulically, and the rare variant also diffused before replicated, and the world may decline and extinction. So to escape such dilution problem, the several possible environment can be proposed to enrich or isolate RNA species. So clay mineral surface is the classical model, and eutectic ice phase is also recently quite attracted. And the core cell bed forms with the complex formation between the negatively charged RNA and the positively charged molecules also give the phase separate droplet. And fatty acid vesicles, most similar to current cell system, may also encapsulate, isolate, and enrich the RNA. Protein, as you can understand in the excellent talk given in the last day, and protein can form the very excellent assembled structure, so with which they can show the more excellent function than the protein monomer. So it also means the self-assembly of the protein provides some condition or environment for their enrichment or isolation. So unfortunately, we can't find natural example of such similar type of the RNA assembly. So our group decided to artificially design similar type of the RNA assembly through the structural engineering of the naturally occurring ribozyme. We used the group 1 ribozyme as a suitable model system for such structural redesign. So group 1 ribozyme originally found as a self-splicing ribozyme. It removed itself from the precursor RNA to join the 5' and 3' fragment to yield the functional messenger RNA. So we can easily modify the structure of this ribosome. So we separate this part and remove the 3' fragment. And this system, in this system, intron part act as true catalyst, and this part serve as a simpler substrate that cleaved at this particular site by this RNA catalyst. This ribosome known to form the complex and defined three-dimensional structure, and it consists of the 3 large structural domains, and we have designed 2 biparticle ribosome system in which each structural domain can fold its 3-dimensional structure in the absence of the rest of the domain, and also these 2 domains can reconstitute the fully active full-size ribosome. So first, we use this bimolecular system to design the one-dimensional oligomer structure of the ribosome. So briefly explain, we first separate these 2 ports, like here, and then connect these 2 parts with introducing the rigid duplex helix here and here, and covalently connect the 2 domains like this. So you can easily understand this is a uniparticle RNA, but these 2 domains cannot form in the active structure in an intermolecular manner, but these 2 domains can intermolecularly reconstitute the active ribosome, so you can easily understand this unit RNA can intermolecularly assemble to form this kind of one-dimensional oligomeric structure. So we compare the catalytic. We first confirm the formation of this oligomeric structure by using the native gel electrophoresis, and then compare the catalytic activity by using the model reaction system to cleave this short substrate RNA. So biparticle ribosome show the activity like this, and the 1D oligomer form shows slightly but distinctly about 2.4-fold higher catalytic activity than the parent biparticle ribosome. More interestingly, so these 2 structural modules assembled using the several intermolecular tertiary interactions. We try to disrupt one of the important interactions. This original interaction formed the 4 base pair, but we completely disrupt this base pair. So resulting mutant in the bimolecular form became inactive. But interestingly, mutant lacking this important interaction still weakly but distinctly active in a one-dimensional oligomeric form. This is the first experimental result that we think the ribosome assembly may some functional benefit to the core structure. So then we use this right side bimolecular system. We use the one-dimensional oligomer with this system, and we then use this second system to form the polygonal oligomeric structures. So in this system, the blue parts contain all essential elements for the catalytic mechanism. So, and the red part serve function as the activator molecule to stabilize the active structure of this core ribosome. So you can see the parental ribosome is highly active to cleave the substrate within 10 minutes. So, but the core ribosome still has the catalytic activity to cleave the substrate, but the catalytic efficiency is much lower than the parent ribosome, mainly due to the instability or the structural flexibility of this RNA structure. But the reconstitution system completely recovers this full catalytic activity. So, but we also see the full catalytic activity can be also recovered by stabilizing this core structure by increasing concentration of the magnesium. This is a clear evidence that core ribosome has all essential parts of the catalytic mechanism. So we use this biparticle ribosome system, and we then connect this activator part with the non-natural portion of the ribosome. So you can see the resulting variant should poor catalytic activity in isolated states, but by optimizing this linker duplex, so we computationally predict that this engineered ribosome can form the intermolecular complex to give the closed oligomer. In this molecular design, we expect the formation of the tetramer. So we can actually see the expected triangular structure by AFM imaging. And we also change the length of the duplex, linker duplex. The 5 is the original design to give the triangle, but we vary the linker length from 2 to 6. And one base pair shorter design. So we examine the extent of the oligomer formation by using the native gel analysis. So strongest band correspond to the expected trimer, and one short linker variant still forms similar band pattern. So we can also show the tetramer as a minor product, but too longer and too shorter linker no more form the closed polygonal structure. Instead, it formed the helical structure. But interestingly, the 2 base pair shorter variant poorly formed the triangle structure, but instead it formed the tetramer or higher oligomer. That might be the pentamer or hexamer. So activity assay also show the interesting 3-fold difference in catalytic activity between the 2 trimeric variants. So original design also showed the highest activity, but the one base pair shorter variant structure formation pattern seems similar, but the activity reduced about 3-fold. And this 2 base pair shorter variant show the higher oligomeric state in the native gel, also show the significant amount of the pentagonal structure in AFM, and it's very rare, but we also confirm the hexameric structure in AFM. So this variant is interesting, but because it can form the tetramer, pentamer, and also hexamer. So homo-oligomerization can form the multiple types of the oligomer, but we want to control the formation of the particular oligomer. So we engineer the interaction interface between this activator RNA and the core ribosome by changing the tertiary interaction. So tertiary interaction can be engineered in a molecular level to change the binding specificity. So we prepared eventually 6 different particular interaction. So we designed a pentamer or heterohexamer. And the stepwise addition of each component, you can see the open trimer, and tetramer, and this is closed pentamer. So AFM image frequently show the pentagonal structure, and this is open pentamer, open form pentamer, simple pentamer, and this is closed hexagonal hexamer. We also selectively conform the structure of the hexamer. So hexamer can be designed from the homo-oligomerization and the selective hetero 6 distinct components also give selectively form the hexamer. But the 2 components also show the trimerization of the dimeric unit weakly form the hexamer. But the dominant form, you can understand the tetramer is much dominant species, and the dimerization of the 3 distinct RNA interface, dimerization of the trimer more efficiently form the tetramer. We can see the structure by AFM. And as we can prepare the trimer, tetramer, and pentamer, and the hexamer in 2-dimensional polygonal structure, we then expand the structural dimension to the 3-dimensional level. So like the beautiful Chi-C protein complex, we try to expand the polygonal structure to the double-decker style, or the like the protein crystal, we expand the polygonal structure to the infinite, to the sheet-like or honeycomb sheet-like structure. So we first try to expand the structure to the 3-dimensionally by making the double-decker variant of the most standard trimer ribozyme. So we simply use the kissing type, heterolytic kissing group interaction to make the pillar to connect the first floor and the second floor. So you can see when we mix the 2 triangle variant having the kissing group interaction, you can see the new strong band corresponding to this double-decker hexamer. So interestingly, when we compare the catalytic activity, double-decker hexamer show the 6- or 7-fold increased higher K observed rate than the parent. This is 3 triangular trimer. So the reason, considering the reason why this double-decker type hexamer show the improved activity than the parent trimer, we consider the possibility that this double-decker trimer can be formed by not only by assembling the 2 trimer, but also assembling this side wall tetramer and the pillar dimer. And what important is of course, this triangle trimer is catalytically active, but this side wall tetramer also formed the 2 fully active ribozyme units. So this also catalytically active. So it means the formation of the 3-dimensional structure has the multiple pathway in which the intermediate also show the partial catalytic activity. So to confirm this path, so we change the trimer part from the homotrimer to heterolytic trimer. So because we have already prepared the heterolytic pentamer or hexamer design and conformation of the trimer is relatively easy. We selectively form the trimers, and efficient formation of the trimer can be conformed by AFM imaging. And also native gel. By using this selective heterotrimer, we selectively construct this side wall, this one, like this. Side wall tetramer can be prepared like this, and we conform the formation of the tetramer in a native gel, and also conform the double-decker hexamer by using the heterolytic triangle trimer. So catalytic activity also confirm the multiple pathway has partial catalytic activity, because the double-decker hexamer show the highest activity, and the triangle trimer show this activity, and the side wall tetramer also slightly higher, but lower activity than the parent double-decker hexamer. So AFM imaging also strongly suggests the double-decker hexamer, because we can see, so this tetramer show more flexible than the polygonal trimer, and show this image, but this is a dimer of the pillar part, so this image is about twice larger than the pillar dimer, and the resulting final hexamer is shown like this, and we have the base of the tetramer and the ridge dimer, and we can see the two bright spots at the corner of here. Then we finally expand our triangle to the two-dimensional structure that might be somehow similar to proto-cellular state. And so we first plan to expand the triangle structure to tetramerize to make the large hexagonal structure in which each corner consists of the RNA ribosome trimer. So totally, this hexagonal structure contains 18 active ribosome units, but AFM imaging, we can't find no such hexagonal structure. Instead, we can find the linear octamer containing the total 24 ribosome unit, or instead of the hexamer, we frequently observe this square structure containing 12 ribosome unit. So we now considering to change the structural design to for the two-dimensional seed from the, we first expect to assemble this hexagonal structure to make the honeycomb-like 2D structure, but now we are considering to design the lattice-like structure by using this square ribosome unit. So, and also we cannot expect the formation of the honeycomb-like structure. We try to assemble this trimeric ribosome with the kissing base pair interaction to form large infinite assembled structure. So by using the heterolytic triangle trimer, we form the assembled structure whose AFM image provides some large globular structure in which we can see many triangle ribosome trimer, and the size of this large assemble is reached to 200 nanometer. And interestingly, this assembled state also shows the several fold increased activity than the parent triangle unit. And this is the final experimental slide of my talk. And finally, we try to oligomerize the homotrimer. This is the simple but most stable triangle nanostructure. And we here use the homolytic base pair assembly that also gives the strongest assembly between the triangle unit. So we expect the resulting assembled structure may not be controlled, but the size must be larger, and the resulting assembly give the very large assembled structure in AFM, and one island size reaches to 1 micrometer, in which we have many triangle structure connected via kissing group interaction. So we expect this structure also give the higher catalytic activity than the isolated trimer, but unfortunately, in the current stage, this island shows the catalytic activity. This is a positive result, but the extent of the reaction is several-fold lower than the isolated trimer. And this is the final slide of my talk. So to concentrate or enrich or isolate the primitive and self-replicating ribozyme or other ribozyme to develop the RNA world, several different types of the enrichment or compartmentalized system has been proposed. But also our research started from the RNA nanostructure design, but it's still primitive, but the several lines of evidence may show the dense self-assembly of the ribozyme starting from the trimer to double-decker, or the such two-dimensional assembly may give some positive effect to the catalytic function of the ribozyme. And also we are considering the possibility that these densely assembled structure may also exist in some stage in the RNA world to contribute its sustain and development. That is my talk, and thank you for your kind attention.
Okay, thank you very much. So we'd like to open the floor to any questions you might have.
Oh, thank you. Great talk. My first question is, what about the assembly and disassembly kinetics or dynamics of this ribozyme, especially for polymers, either one-dimensional or some other somehow symmetrical forms of the polygons? So is it fast exchanged? Or once isolated chemically, are they rather stable for a while in solution?
It's very important question. And so such domain or module assembly, also in the ribozymes, for example, for example, parent system, so biophysical analysis has extensively performed to measure the stability of the dynamics of this domain-domain interaction. So we should consider and analyze such property in our polygonal or double-decker system, but we cannot perform such kind of experiments. And the other problem is so to measure the AF imaging or the native gel, we need certain level of the stability in the complex. So we typically use the 10 to 15 millimolar or sometimes 20 millimolar magnesium. Magnesium ion generally stabilize the structure and assembly of the RNA, structured RNA. So, but in this system, that is the bottleneck or weak point of this system. We want to link the structural information and the catalytic activity. But in this system, catalytic activity is exhibited much lower magnesium ion concentration. This due to so structural analysis, we need a stable structure, but the catalytic activity easily exhibit, but relatively weak and transient complex.
Okay.
Okay.
So, okay.
If we have time, we'll return.
Thank you for your interesting talk today. And I have one naive question. What's the yield of this double dagger or hexamer system of RNA assembly? This RNA assembly depends on the complementary sequence hydrogen bond, and this hydrogen bond based system always have this equilibrium, dissociation, and association system. So I wonder that the yield of these hexagonal or hexamer systems.
So basically, it depends on the thermodynamic stability, and we have to. This complex formation is not depend on the secondary structure, but the tertiary interaction you may know. But so the control of the interaction may not perfect, but generally the interaction between this this bimolecular system is the binding affinity is rather strong, nanomolar level, and we typically use the micromolar level RNA concentration. So theoretically, equilibrium should shift to the complex formation. But practically, the assembly control is not perfect, but
Thank you.
Okay, thank you very much. Unfortunately, we do not have any more time right now. I encourage if you have any further questions to discuss during lunch or during one of the breaks. So let's thank the speaker once again.